Okay, so let's just dive right in. We're all surrounded by fluids, right? Water, oil, the coffee you're drinking, and most of them behave pretty much exactly how you'd expect. But some, well, some are just plain weird. Today, we're going to pull back the curtain on the secret life of these weird fluids, things that look simple but hide this incredibly complex physics that stumped engineers for decades. Until now.
So let me ask you this. It sounds like the start of a really bad joke, right? What do tomato paste and molten metal actually have in common? Well, believe it or not, the answer is the key to building stronger, safer, and way more efficient products, from the car you drive to massive oil rigs. Stick with me here, because this connection is a much bigger deal than you could ever imagine.
All right, let's start with the big mystery. Take a look at the left. That's a normal fluid flowing through a pipe. See how it's fastest in the middle, and then it kind of slows down in these nice, neat layers towards the walls? Classic stuff. Now, look at the right. That is a weird fluid. It's moving with this solid-like plug right down the center. It almost looks like a solid rod being shoved through the pipe. So what on earth is going on here? To really get that difference, we've got to unpack the physics of how things flow. We need to talk about the two very different families of fluids at the heart of this whole story. So on one side, you've got your Newtonian fluids. These are the predictable ones, the ones that follow the rules, like water or totally liquid aluminum. Their defining feature is that their viscosity, their thickness, is always the same. But on the other side, you've got the rebels, the non-Newtonian fluids. These guys are completely unpredictable. Their viscosity isn't some fixed number. It actually changes depending on how much force you put on them. And yeah, this is where our tomato paste and semi-solid metals come into play. Let's just lock in on that key idea for a second, viscosity. It's really just a fluid's resistance to flowing. For something like water, that resistance is constant. It doesn't matter if you're stirring it gently with a spoon or blasting it out of a fire hose, it's still water. But for a non-Newtonian fluid, that resistance can change like crazy. It can be super thick and stubborn one second, and then thin and runny the next. It's a moving target, and that's what makes them so hard to deal with. And this graph shows you exactly what I'm talking about. See the vertical axis? That's viscosity, or how thick the fluid is. And along the bottom, that's the shear rate, which is just a fancy term for how much force we're applying, like stirring or pushing. Now watch what happens. As you apply more force, the viscosity just completely nosedives. It gets thinner and thinner. This is a behavior called shear thinning, and it's the signature move of these weird fluids.
Now, you might be thinking, okay, cool science trick with ketchup. But in the world of heavy industry, this unpredictability isn't just some fun fact, it is a massive, often billion-dollar engineering headache. Why does it matter so much? Because these fluids are absolutely essential to some of our biggest industries. We're talking petroleum drilling, moving oil and gas through pipelines, chemical manufacturing, and even creating high-strength metal parts for cars and airplanes. In these fields, if your calculations are wrong, if you can't predict how a fluid is going to flow, you are looking at costly and sometimes really dangerous failures. So here was the fundamental mistake in all the old engineering models. They were built around a key number called the flow index that was supposed to describe how a fluid behaves under pressure. And for simple fluids like water, that number is constant. It never changes. The huge mistake was assuming that it was also constant for these weird fluids, but it's not. For them, that value is always changing, and that's what threw all the predictions completely out of whack. And this is where the big breakthrough comes in. Researchers finally developed a new, much smarter model that can actually predict the unpredictable. They cracked the code. So how does it work? Well, it's this new, generalized process. First, you pick the right mathematical model for the specific fluid you're working with. Next, you calculate the forces that are happening right at the pipe wall. But step three is the secret sauce. This is where the new model calculates the true non-constant flow index, taking into account how it's always changing. And once you have that real number, step 4 can tell you the precise pressure loss, letting you predict the fluid's behavior with just incredible accuracy. And the researchers who created this knew they were onto something huge. They said that their model would lay a foundation for using way more precise models in day-to-day engineering. Basically, this wasn't just a minor tweak. It was a total game changer in how we can control these materials. But, theory is one thing, seeing is believing. So let's head to the lab for a little visual showdown. We're going to see what this difference actually looks like in action. Welcome to the Great Fluid Race. All right, first up, we've got our predictable Newtonian fluid, water, which is acting as a stand-in for liquid aluminum. It's getting shot into this clear mold at a really high speed, just like it would in a factory making car parts. So far, so good. And there it is, complete chaos. The flow just breaks down. It starts splashing everywhere, it gets turbulent, and this is the critical part, it traps huge pockets of air. Now, in the real world of manufacturing, those air bubbles become weak spots in the final metal part. They're defects. This run is a total failure.
Okay, let's reset. Now it's time for our non-Newtonian champion, tomato paste, which is playing the role of a semi-solid metal. Right from the very beginning, you can see it's moving into the mold in a completely different way. Just look at that. The control is absolutely perfect. The tomato paste moves forward as the single, stable, predictable front. There's no splashing, no chaos, no trapped air. It just smoothly pushes all the air out ahead of it, filling every single nook and cranny of the mold. This is exactly what engineers dream of. And here it is, the side-by-side that says it all. On the left, you have chaos. Air bubbles and uneven fill, that's a weak, useless product. And on the right, you have total control, a clean, perfect fill. The difference is just night and day, and it all boils down to that one simple idea, a viscosity that changes. So, let's connect all the dots now. We've seen the theory, we've seen the new math, and we've seen the tomato paste prove it visually. Now let's talk about what this means in the real world, the actual impact of getting this right. This table basically shows you the proof in the pudding. The columns in the middle compare the actual pressure they measured in a pipe with what the new model predicted it would be. But just look at that column on the far right, the percent error. We're talking about error rates as low as 0.2%. That is practically nothing. It means the model works, and it works incredibly well.
And that kind of accuracy has huge payoffs. It leads to safer, more efficient oil drilling. It means we can make stronger, lighter, and totally defect-free metal parts for everything from cars to airplanes. It means less waste, less energy, less cost in manufacturing. At the end of the day, reliable predictions just mean better engineering for everyone. And here's the really wild thing. This isn't just about factories and pipelines. These non-Newtonian fluids are literally everywhere. The paint on your wall. It's designed to be thick in the can but thin out as you brush it on. That's shear thinning. Even the blood flowing in your veins has these same weird properties. Understanding this stuff helps us in ways we don't even think about.
And that brings us to one last, really fascinating question. Now that we're finally starting to master these materials, now that we can actually predict their behavior, what's next? What kind of new technologies, whether it's in medicine or 3D printing or something we haven't even dreamed of, are going to be unlocked? I think the possibilities are going to be just as surprising and as cool as the fluids themselves.